It's good to be a last speaker day today. That I heard the next speaker cancel the talk. I guess everybody anxious to go to the boat cruise, just rush through. So don't ask any questions. Today I'm basically talking about the surface morphology of a cobalt catalyst. And we heard a lot of talking about the mechanism and kinetics and theory. That rarely don't talk about how to make a catalyst and different catalyst preparation methods, how impact and cause a difference to the catalyst morphology. Today I want to focus on the preparation methods and the effect of preparation methods to the cobalt catalyst. And when you're talking about cobalt catalyst, the first thing you think about probably that lots of cobalt catalysts available in commercial scale and for many different reactions, for hydrogenation, for emanation. And we typically see that the emanation of a C2C18 alcohol, that's cobalt catalyst, and hydrogenation of a C3 and a C18 aliphatic aldehyde ketone, that's cobalt catalyst also. And also hydrogenation of nitroamine, that's cobalt catalyst. So at the start, people were thinking about cobalt is cobalt, we're just throwing the typical emanation and hydrogenation cobalt catalyst to Fischer-Tropsch. What difference it will make? That's probably a good start if we ignore the mechanism and kinetics, just to do the blank search. So here's the first one of the catalyst, and we tried in this SCI G62, the typical cobalt catalyst for emanation. This is a genetic FD catalyst. Actually, we just take some literature example and make the catalyst according to literature data. And you can immediately see that there's some difference those two catalysts in property. It's tricky to do this. The first, actually, the commercial catalyst for emanation, hydrogenation, cobalt level is 41%. Those typical catalyst probably we want to use for Fischer-Tropsch is 20 to 30%. And the cobalt reduction is a little bit lower at, say, typical temperature 350 degrees C, but not that bad. And cobalt dispersion is really pretty low and compared with the typical dispersion for Fischer-Tropsch catalyst, which we heard about the 5 to 10%. The BT surface area is pretty low and compared with typical Fischer-Tropsch catalyst. The pore volume is low, and also more remarkably, actually, pore size is very large, and compared with the typical Fischer-Tropsch catalyst. Then look at the relative Fischer-Tropsch activity, and this so-called genetic catalyst will get 6.31. Then this amine emanation catalyst, G62, it's very low and activity. So that looks like you're just throwing a cobalt catalyst into Fischer-Tropsch, not necessarily working. So that got to be something into catalyst preparation. By the way, both catalysts we promote at the same time promoter. Then as simple as lots of people are talking about rational catalyst design, and you need to consider the mechanism, and then you actually come up with a set of composition, and consider just structure sensitive versus structure insensitive, and consider the electron, the modification, and also look at the kinetic part and what the structure requirements, is this diffusion limited or not limited. Then more important, I will talk about based on those requirements, what really preparation methodology or technique will be more appropriate for this Fischer-Tropsch catalyst. Then, of course, everything going to be a reality check to see how good, how bad it will be. The first, just briefly look at this mechanism for that emanation. And you can immediately see that drastically different from a typical Fischer-Tropsch catalyst, which is polymerization, as simple as I say that this alpha-T emanation is well known. Actually, that the first step is a slow step, actually hydrogenation on surface. Amine species from amine is probably pretty fast. So it maybe not need lots of a cobalt surface, and then this is really we want to emphasize on. That's why we see that. Plus, this is not the form high molecule, just simple condensation of aldehyde intermediate with ammonia. So that the pore size distribution and pore requirement probably not as the stringent requirement as actually Fischer-Tropsch. Also, the cobalt dispersion is not need as high as Fischer-Tropsch. Now this is a simple picture of the Fischer-Tropsch. Everybody knows this is just polymerization. You CO deassociate, and you keep adding on methylene group, and you actually eventually get either dissolve extract hydrogen from the olefin, or you hydrogenate from the parafins, or you actually can add a proton to form directly to the parafin. So that's two mechanisms is vastly different. Then look at this kinetic consideration for the Fischer-Tropsch, and I took this from Professor Hans Schultz, and probably 13 years ago, the paper, and talking about the kinetic consideration, and this is a fast step by chain growth, and termination to the olefin is slow, but to the parafin even slower. So though maybe there's diffusion inhibition or diffusion enhancement actually involved by we change the pore size distribution here. Really, I'd like to address here is the following. And first, what is a physical requirement for the cobalt catalyst in the Fischer-Tropsch reaction? Then this chain propagation can be regulated, enhanced, or inhibited by changing those sets of physical property. And my focus again will be more focused on the preparation technique, and the technique play a role here. I think the answer is yes, the positive, but how we do this. And I just give you some brief idea and how we can accomplish this. Based on the different preparation technique, and here just give you a ballpark actually numbers, and we can come up with a Fischer-Tropsch catalyst with the following property, and promoter can anything from precious metal, cobalt typically 15–30%, and cobalt reduction again at 350 degrees C. It depends on technique of preparation. I'm not talking about the actual promoter effect. I have seen promoter, but just by actually changing the preparation technique, you probably can reduce the 50–90% of cobalt. Then change your oxidation number. That's obviously you can, based on that number, you 1.3, 2.4, and from cobalt 304 to cobalt 0, the maximum change of a number is 2.7. Your 2.4 is pretty much 90%. Then XRD in cobalt 304 at the 50 to 200 angstrom. That depends on preparation technique again. Then cobalt surface area and 4 to 10 square meter per gram dispersion, and 5 to 9. Then also that there's a whole set of structure property, and we can change it by changing the preparation methods. And CBD, that's something we need to consider in the industrial reactor, 1.0 to 1.4 gram per cc. We can change then the BT surface area 60 to 220, and the pore volume, and this thing, the average pore diameter, I will talk about more. But again, different methods can give you 50 to 110 angstrom. Then another thing I will talk about a little bit about fractal dimension. Fractal dimension basically measures how rough and how smooth your pore is. Then actually, fractal dimension 2 is a flat surface. It's 3 enclosed pores. So typically we measure 2.2, 2.6 for the Fischer-Tropsch catalyst. But then how we change it from 2.2 to 2.6 or vice versa. And the particle size of this slurry phase catalyst typically average 80 micron, but it depends on how it's spray drawn. You can do 40 to 120 micron. Back to the preparation, how we actually change those parameters, and typical preparation methods we use for the this type of Fischer-Tropsch catalyst by impregnation. Everybody talking about cobalt nitrate. and sequential impregnation 3-4 times, you get 20 to 30%. When you're talking about impregnation, there are three things we need to remember that's important for impregnation. First is the acid electrical points, or point of zero charge of the oxide. That's actually intrinsic property of this aluminum or titanium or zirconium, wherever you put on. And second is the pH impregnating solution, and you can be acidic, it could be actually basic, or could be something between. And actually, what's the charge of ion that will be absorbed, and is the ionic, or this is the cation ion. So the other general rules, if you actually oxide have say certain that PZC, then actually if your impregnating solution, pH of impregnating solution is lower than PZC, then the actual surface you more tend to actually positive charge. Then positive charge you probably will be more tend to absorb, and more negative charge to the actually absorbing ion. So that's actually this is a basic principle of this impregnation. Then we can play around with the PZC, play around with the pH, and play around with the nature of the ion we want to absorb. I just listed some guidance. This is just a very rough guidance, and give you some rough feeling about the absorbing strengths. That depends on your pH of solution and what the actual nature of the ion. And for example, in the case of everybody uses cobalt nitrates on the aluminum, for example, aluminum typical PZC is somewhere between 7.2 to 8. Then cobalt nitrate is pretty acidic, say that the 2 or even lower. So in that case, actually, you have a cobalt which is the cationic metal compounds, actual metal ion. Then actually you absorb on the pH less than PZC, then you're actually pretty weak, and so then when you're sintering, then you probably it's easy to be sintered. Then if you change the pH of absorbing solution, then you actually change it from acid to the basic, you probably get the more strong absorption, then you're actually difficult to be sintered cobalt. Then based on some of those thinking, and so we come up with some the general consideration. We try this approach to see if it works, and this which is non-acidic impregnation. Then we choose the larger ionic radius compounds, not necessarily just a simple cobalt nitrate. Then here is actually some observation after we choose the 3 different the methods of preparation, which actually involve a different pH of the impregnating solution and different radius of ionic species. And then immediately you can see this green line. By the way, this is from hot XRD, hot stage XRD, which means in situ, you heat the sample in the XRD and simulate calcination. And then this is the x-axis temperature, and the y-axis this is the cobalt oxide crystal size. You can immediately see this green line, which is actually the lowest pH and the smallest ionic radius. That gives you a very rapid crystal size increase, and upon the heating. And then those 2 methods here, one the yellow line and red line, represents different methods, which are the more basic than actually this first methods, and have a larger the ionic radius of impregnating species. They give you actually slower increase of cobalt oxide crystal size. So that seems that the indication, our actually prediction, our actually theory seems on the right track, and seems at least at this point, and by using non-acidic environments impregnation, by using larger ionic species, seems to give you actually more thermally stable and cobalt oxide at this point. Then next thing that we check is put this in the SEM and see what's the difference. This is, again, the method A is this non-acidic impregnation, And this is our actual pattern technique. It's different from typical cobalt nitride impregnation. And you can see this is typical and the cobalt and the catalyst particles. And you see actually former and speaker, last speaker actually, he presents some SEM picture also. But you can see that immediately you can see some different features here. And he's actually a picture even with ruthenium promotion, you still see that pretty sketchy cobalt and very rough surface, and see the agglomeration of the cobalt. But this is a really smooth surface. As smooth as you can see it like infant skin. Also, you can see this is more like a spiritual and very round spherical particles instead of the granular, irregular shape. So it looks like this is pretty good stuff from just your instinct just by look at physical appearance here. Then as a comparison, this is more like this last speaker presentation that he showed us the typical particle from a cobalt nitride impregnation. You can see that we identified that there's light spots that's actually concentrate the cobalt segregation here. You can see that the very rough surface and lots of segregation and aggregation, and that's tell you that the different catalyst propulsion methods and seems to give you not only thermal stability difference, also the appearance difference here also. Then we look actually in more actually closely, and we put this catalyst, two different catalysts in a real calcination atmosphere, which typically and you calcine in the air, and then we actually increase temperature to low temperature to the as high as 550 degrees C, and that catalyst with rough surface area, with rough surface and conventional impregnation methods, you got a larger cobalt oxide crystal size, but this one with the smooth surface with our own methods and non-acidic environment impregnation, you're starting with a smaller cobalt oxide crystal size, that you remain small, even to the 500, almost 550 degrees C. And that's, again, seems to give you something different. Again, that's this point. And then look at surface area. What happened to surface area? The surface area, this conventional methods give you actually small surface area, and then this is own methods, we actually heat to the 550 degrees C, still much higher surface area than actually begins temperature, the surface area using conventional methods. Not only crystal size, even the BT surface area, and give you a difference. Then people probably will question how actually this will happen. How can this affect the BT surface area? And I probably won't get to the details, but probably in the future, if a patent is issued, probably we can discuss some more detail on this. Then another thing people probably will wondering about, even with this 80 micron particles, is cobalt on the surface of cobalt is so all the way to the interior. But my personal think that that's for 80 micron, that's more like academic than actually real. If it's 2 millimeter, maybe round in the surface. But anyway, in preparation A, again, that's our own methods, B, and impregnating methods. And you can see that our methods is understandable, actually, very uniformly distributed throughout the whole particles. And the cobalt concentration on the surface and in the interior almost same. But typical nitride impregnation, you have a very low in the interior, pretty high on the exterior. So that's another difference. Then we did some theoretical calculation. That's schematic presentation. What probably will happen to the cobalt penetration. And for our methods is pretty much throughout all the way and at least halfway to the interior. And you can see from SEM actually, you can pretty much verify this calculation. And cobalt average is probably 0.21 on the surface, and then it depends on which spots of the surface you could be actually really don't have any cobalt, probably have more in the interior. So you have a very inhomogeneous situation for typical nitrate impregnation. Okay, then this is we just talk about the difference of preparation methods to the physical property difference. Then let's look at in more details of the fine structure of the pore, how this preparation method will affect this pore structure. Then to start with, I give you some fancy picture of this probably presentation of or imagination of the pore. And this is actually, the picture is taken from computer graphic simulation fractal surface. Then you can see that there are a couple of features of fractal surface. One is actually surface is really not actually continuous smooth surface. It's really that the fine structure and that the pores inside the pores inside pores. So when you can imagine when you actually have a probe molecule, using a probe molecule, the molecule size getting smaller, probably we discover more surface. It's the same phenomena we heard a lot about British coastline, US coastline, Atlantic coastline. If you use a smaller lunar scale, to probably you discover longer coastline. This is the same phenomena that we call the fractal. And in the most time, we just simplify as a series of spherical pores. That's a simple situation. But in the real situation, actually, you probably will discover it's not a smooth pores, a bit more like more than two-dimension surface with the curves, with the roughness on the surface. Then actually, another thing I'd like to mention, the roughness in this scale is different from the roughness we see on the SEM. That's actually on the micron scale. This is more on the 10 angstrom scale. So I will present some facts later on. You can see the difference there. Then to give you a little bit of flavor of the fractal dimension, and that's a reason for the fractal formation. And for the typical material and we formed like fish hook material, you involve lots of the steps during the preparation. The more steps involved, the more random process involved, probably you will see actually complex surface. Secondly, why is a fractal, what the fractal means. But I think the fractal dimension will actually give you actually a single numbers, which will tell you some of the features that the other number won't tell you. So in this case, the complexity of the pore is captured by the single numbers and can tell you the occurrence of the same feature at different level of the resolution. And we probably can use the fractal dimension and can actually very loosely say this is the roughness of the surface. Use that number. Then what is in real situation, what the fractal dimension look like for different material. You're from a simple carbon black, you pretty much get the very flat surface 2.01. And you go to the zeolites, and you pretty much get a 3. And fish hook, just something between. And for example, this apatite, this is probably similar to the chemicals from our teeth. It's pretty complicated material, and we got 2.68 here. Okay, then how we calculate the fractal dimension? Actually, that's pretty simple, and that's a fundamental correlation between actually and the dimension and number of the particles on certain surface. That's actually inversely proportional to the d, which is the fractal dimension. Then we got that relationship, and we can actually do some simple mathematical manipulation, get this 3 minus d relationship. then actually the correlation between the thickness of a surface or dimension of the surface versus actual relative absorbing pressure. So you actually correlate all together, you pretty much can get your D numbers by just notching multi-layer absorption. Okay, then here's the calculation, here's the results. Morphology, we're talking about SEM again here. We can see carry is smooth and sample A is smooth, sample B is rough. Then factor dimension, then we calculate based on the nitrogen multi-layer calculation. And the carrier actually got the 2.5. That means actually microscopically, the carrier actually pretty rough and in the pores. Then the sample A is our own methods proportion. Actually, that factor dimension decrease from the carrier, 2.23. Then the sample B is pretty much similar to the carrier, which you get the pretty rough pore structure at 2.55. Then again, you can see some also the mean pore size difference. And sample A is 57, and sample B is 100. It's a little bit lower than actually original carrier mean pore size. Then people probably will ask a question: is this factor dimension something related to the mean pore size? To check if that's related or not related, I just run 20 or 30 different samples and try and see if there's correlation. If for correlation, why you want the factor dimension? Just use simple the pore dimension. Then it seems that there's no correlation. It seems that from this graph seems to tell you a factor dimension that tell you something different from just average pore size here. Then maybe if you're stretch your imagination, maybe you say that another group of sample here, another group of sample here, maybe this is due to something else, maybe proportional methods again. I need to explore this further. Okay, we have a factor dimension definition, have the numbers, and we're convinced that something independent, not actually correlate with the pore size. Then what this tell us in the real reaction? A couple years ago, Belgian professor Froman actually he wrote a nice paper about the factor surface on the reaction rates. Actually, he checked on a real catalyst system, which is actually the catalytic reforming reaction. He used platinum, rhenium, the typical catalyst for this reaction. Then he come up with two scenarios. And first scenario is say that the carrier is fractal, but that is the active side is not non-fractal. In that case, actually, based on his calculation, the reaction rates of that situation will be actually lower than non-fractal carrier. So then what happened to the second case? Both actually active side and the carrier is a fractal. In that case, actually, this reaction rate will be faster than this reference sample, which is the non-fractal on the carrier and active side both. So from his actual calculation and extrapolation, seems that tell you something factor dimension can affect you actually, and the reaction rates also. Then moreover, he also developed this nice graph and indicate that the maximum of yields correlate to the certain factor dimension. And in his case, 2.6 give you a maximum hydrogen yields, and for this particular naphtha reforming, use platinum, rhenium, aluminum catalyst. So his actual research and found that really factor dimension tell you and something which is related to the reaction rates. It's not just superficial, that's a number. Then that's his calculation, his finding, and what about us then? And we put those two samples in Fischer reaction. This is we run this in CSTR reactor, and you can see that again the A type is our own catalyst preparation method, B typical cobalt nitrate impregnation. And this A type of preparation methods, and for C5 plus selectivity, seems to give you actually roughly 8% at 300 hours, and 8% more of C5 plus, and give you a higher selectivity. The data may be a little bit sketchy, but all the way through you can see that give you actually high C5 plus selectivity, this propagation methods. Then we look further, what about the C19 plus selectivity, and which have a high molecular weights. Then we see more actually striking difference between those two catalysts, and you get actually even higher and selectivity with A type of the propagation methods. And that seems that that's the most stable also. Again, there's some scattering, the general trends there. So that for C5 plus selectivity, you're getting 5% or 8% more than for C19 plus, you get 22%. So, so that actually the facts and associated with the thermal stability of the catalyst, and also associated with the SEM observation, seems we get the catalyst a little bit different from just use the cobalt nitride, the conventional preparation methods. Okay, then here is a very simple conclusion from the simple experiments. And first, morphology indeed can be modified by what we call so-called non-acidic preparation technique, which give you actually catalyst with a more homogeneous cobalt distribution, and highly thermally stable crystalline size, and high surface area. This seems the smaller pore size and a lower surface refractive dimension, which means smooth pores of the catalyst appear favorable to formation of long-chain hydrocarbon. At least this is the initial activity, which has worked 10 days. So as a pragmatic scientist, I have to promote our company. I cannot live here without promoting our company here. This is the Sukimi catalyst. In our GTL process, I took that picture in the Sasso Segunda plant. That was sunset time. It's much better looking at the original picture. My photographing technique is pretty good, actually. So this is the syngas part from Sukimi. We can offer all kind of syngas catalysts for ATR reactor and for different type of reactor. And then we have this FTCB, FE for the cobalt and iron catalyst for Fischer-Tropsch. Then we have a C79 for methanol synthesis. Apparently, started with a gas, you can make CO hydrogen, make paraffin olefin, you can make methanol, you can make DME by dehydration. Here, that's just the refinery part. You can make gasoline from wax, from different stream of paraffin and olefin. So that Sukimi actually can offer all the catalysts, and except the Fischer-Tropsch catalyst part, most other part that we can offer actually commercial scale catalyst. Then last but not least, acknowledgements for the people helping and to preparation of sample and catalyzation. Thank you for your listening, and I'd like to answer your questions.
Any question, remark, or comment?
Yes, I just want to go closer. Okay,
just to start, I think in your conclusion, I'm not quite sure that you said that if you have a smooth pore side inside, the hydrogenation or whatever changes. What was exactly this sentence?
The favorable to the long-chain hydrocarbon formation.
Yeah, it is favorable to formation of long-chain hydrocarbon.
Right.
Do you have any explanation for this?
Smaller pore. First, small pore probably to actually expect that you actually have a more diffusion limitation, and you're probably more favorable to the olefin reabsorption on the surface. Then I think a smooth pore also is similar to and smaller pore size effect, but properly preventing actually further diffusion of the the products from the pores. But I'm not sure what really this smooth pore means here. But that's just the initial primary observation right now.
Thanks very much. And to my best knowledge, the authors of the last talk did not see that. Anybody? So no more about paper, we are quite saturated. So thank you very much for the lecture and for the participants.